You will learn so much about Triton. If you are just a beginner and you don't know anything about coding Triton, after watching this video, you will learn step by step, every single function step by step, and you will be able to code this whole thing. So this is Kernel Fusion. You will learn absolutely everything. First, I will import Triton in Google Colab, and then we have this at triton.justinTime, and we define some functions. So that's gonna be the kernel that executes on GPU because we have this just-in-time decorator. So then we will import triton.language as TL, and here I'm gonna just add this PID is equal to tl.programID 0. So this program ID of 0 gives the current program thread's ID along the first axis 0. We'll try to change this later and see what happens. Triton launches many programs threads in parallel. Each one gets a unique ID. PID is an integer like 0, 1, 2. Then let's add this part. Launch the kernel with 4 parallel threads programs. And we will see what it means. So we say my kernel and grid and pass in number 4 and we invoke the function. Let's see. The name grid is not defined. So actually, this was just the explanation that we pass in grid of 4, but this was not defined. So the way we define this code is properly is like this. Pass in these brackets and 4, comma, and then nothing after comma. So this will work. This will launch. Let's see what this will do. Successful execution. We got this compiler working and the kernel is compiled. So why are we using 4 comma? Why are we using comma? Because 4 is just a number, but this is a tuple. 4 comma is a tuple with one element. Needed because Triton expects a tuple of grid dimensions. So 4 comma is a valid tuple, 1D grid with 4 programs. 4 comma 2 is 2D grid with 4x2, 8 programs. But just 4, this is not a tuple. So you can use just one dimension in the tuple when you have data as a flat 1D array. For example, we have this just 1D array, and then you can create a kernel with just one dimension. Each program processes one or more elements, okay? So when to use 2D grid in your kernel? When your data is matrix-like, for example, batches of rows, tiles of matrix, or multiple sequences. For example, we have batch and sequence. So we have grid, batch, and sequence. Then this is a tensor, 2D tensor. So then tl.programID 0 gives batch index, tl.programID 1 gives position within the batch or within the sequence. This is very common in attention, matrix multiplication, or any situation where your kernel needs to process blocks, tiles of data. When to use 3D grids? When you simply have 3D data, so for example volumes, 3 dimensions, batched 2D tiles, like video, image batches, large math multiling. Actually, we have this 3D data mostly in LLMs because we have the vector embedding for one token and then sequence of tokens, that's 2D. So sequence of tokens is our context window. And then multiple context windows in a batch, so that's 3D. Usually we have it like that. So let's go here to our kernel and below create this output tensor of 4 elements. And let me import torch. So we have torch empty, 4 elements. Let's do that. So if I just print output, we have this 0, 0, 0, 0. And device is cuda 0. So this is the first GPU and we have only one GPU. And data type int32. So here we have 4 length and 4 length. So we have 4 length. So we will define 4 length of the kernel. And we will pass in this output like that into this kernel. So this kernel will receive not output, but output pointer. So this will be a pointer in the memory where this, in the GPU memory where this is stored. So let's say I'm gonna add this line. So this is tl.store. We want to store this ID of the program into memory as well. And we will store it at output pointer plus PID. Oh, okay, let's explain this line of code. It's a bit tough. So we have tl.store. This stores a value into global memory. For example, your output tensor on the GPU. Think of it like output PID is equal to PID. This depends then on the value of the PID. So if the value is 2, this will store at index 2 in this tensor. It will store the value 2. If the value is 3, it will store at index 3, it will store the value 3. But done in Triton, low-level style for raw memory addresses. So we can take a look at this output pointer plus PID. This calculates the memory address to store the value at. Output pointer is a Triton pointer to your output tensor in GPU memory, plus PID offsets the pointer by PID elements. So if PID is 0, store at output pointer 0, 0, so the first element with 0 index. If PID is 3, store at output pointer 3. This tells each parallel thread where it should write its result. Let's see what this PID is actually. This is the value we are storing. It's the program ID. So each thread just writes its own ID to memory. So this means each thread writes its ID to its own index in the output tensor. Yeah, so each thread has its own index and it will write according to that index in the output tensor. If you launched 4 threads, you'd get the result. Output is equal to 0, 1, 2, 3. Each thread says, I am the thread K. I write K to output of K. So yeah, if I run this, we will just see 0, 1, 2, 3. So if I delete this, because we are converting it to GPU, so let me just do it like this. 0, 1, 2, 3. So, but what if I say here 1? I think it will throw an error. No? What? By the way, I'm learning with you, so let's see what happens if I write 1. So why it works in Triton, TL program ID axis gives the program ID along a given axis. So when you wrote TL program ID 1, you are saying, give me the program ID along axis 1, okay? But there is the trick. You launch the kernel with shape 4, which is 1D grid. Triton automatically fills missing dimensions with 1s. So this, my kernel 4 output, is same as 4, 1, okay? So the program ID of 0 goes from 0 to 3, 4 threads. But program ID of 1 is always 0 because the size is 1. So this should be 0, 0, 0, 0. But look, we got 0, 1, 2, 3. Which is crazy. Maybe if I define different output. What? So it looks like the Triton swaps access when compiling the kernel, flattening the grid if you only index with program ID 1. So it looks like instead of, because we defined as 4 comma, the Triton will treat it as 1, 4 because we are looking into the second dimension. Yeah, but if I explicitly add 1 here, now it's gonna be 0, 0. Now there is no conversions. Yeah, so I think if I just put it 1 dimension but try to access the second dimension, then it's gonna treat this as the second dimension. It's gonna swap. But if I explicitly define 1 as second dimension, then it's gonna be, yeah, wait, what? What? Now, bro, I had it on video. I have it on video. Before I did the same thing. and it was 0, 0, 0, now it's 0, 1, 2, 3. Maybe it stayed in memory or something. Okay, so if I put 2, but I have 4 and 1, it's gonna be 0, 0, 0, 0. Because this is the third dimension, but we only have 2 dimensions. If I do it again, it's 0, 0, 0, 0. Okay. If I put 3, now this is an error. Okay. I guess I can only extend by 1 dimension. So weird, I swear, it's so weird. So if I have 4 only and I put this, it's gonna be error. If I have 2, so this is still extending by 2 dimensions. 2 works. Okay, I think I figured it out. I think it will always treat this first dimension. Yeah, okay, so if I run this 2 times, the first dimension, first time it will be 0, 0, 0, 0, second time it will be 0, 1, 2, 3 for some reason. It's so weird. I swear it's so weird. So we got some weird behavior here. Let me just show you the weird behavior. If I flash this, delete, I think it doesn't matter. So if I just have 1 dimension and I try to access the second dimension, it will treat this, it will somehow extend this first dimension into second. I can also try to access the third dimension. It will put zeros, zeros, no. Okay, I don't know what's happening. If I try to access fourth, now it's error. Yeah, now you can access first 3 dimensions always for some reason. Well, what if I increase number to 5? Yeah, it doesn't work. Okay, if I put third dimension, 0, 0, 0, but if I run again, 0, 0, 0. Okay, so I ran 2 times and now it's 0, 1, 2, 3. That's crazy. If I run this once, but next time I run, it's gonna be 0, 1, 2, 3. I don't understand it. Let's just go to the next thing. This is complex. I feel like it's doing something with the dimensions as I run it. So it's maybe changing the tensor or adding something in the memory. Next, let's add this variable block size equals 4. So now each thread will process 4 elements, not just 1. So before we had 4 threads, each processing 1 element, and it was writing ID of itself. But now each one of them will process 4 elements. So we need to tell it how to traverse the memory. So here we have this offset. So offset is going to be equal to the PID. So if we have 4 threads, PID is going to be 0, 1, 2, 3. So the first thread, we want to process first 4 elements. So we will start with 0 times 4. So that's going to be the beginning offset. So it's going to be 0. Plus tl.arange. So we will create a new vector from 0 to block size, which will be 0, 1, 2, 3. Yeah. So this will go from 0 to 0 plus block size, going 1 by 1. Okay. For the second PID, it's gonna go from, so 1 times the second PID ID is 1, so 1 times block size. So it will just move by the block size and then go here from each element from 0 to block size. And then for the third one, it will move again by the block size and go elements by one here when you add this array. So we say TL.store output, so this is the beginning output pointer, plus offset, which is going to be calculated here 1 by 1, and we will store the offset. So here we will create an output tensor or vector of 16 elements, because we will have 4 threads, each processing 4 elements. Let's see what happens. Error. So the problem is this block size needs to be known at the compile time, when the code is compiling, not just later at runtime when we have these variables. Why Triton needs it? Triton just-in-time compiles your kernel like an optimizing C++ compiler. So if you say this, it needs to know exactly how big that range is before generating GPU code. So block size must be constant when the kernel is compiled, not a runtime variable, because this is compile, needs to know it while compiling it. So what we need to do is, when in the kernel definition, we need to define it with this type constant expression, tl constant expression, and you pass the value from the outside. So block size 4 when we are creating the kernel, I'll show you. So here, when we are creating the kernel, we need to pass block size 4, and we need to get that variable here. So now it's gonna have access to it in the compile time, at the compile time, and we don't define it here within the function. So you can actually define variables within this function, like this one. It will work. But the problem is you cannot use this variable for things like this, where it needs to know the size of the threads and variables, how many threads to allocate, how much space, memory, etc. Because it's doing that on the compile time, so it needs to have this variable at the compile time. Here we have numbers 0, 1, 2, 3, 4, 5, 6, all the way to 15. So I guess if we store offset minus, or let's say plus 1, it will go from 1 to 16. So let's understand this a bit better. So we have number 4 here. So this means you are launching a grid with 4 parallel Triton programs, threads. Each program gets a unique PID from TL program ID 0. So this just means we have one dimension. 0 means just we have one dimension here, 4. And within that dimension, the first dimension, we only have that one. It's gonna be either 0, 1, 2, or 3, the ID, because we have 4 of them in total. Then we have this tl.arange 0 to block size. This gives each program a vector of 4 indices. So 0, 1, 2, 3, for example. But this just gives a vector of 4 indices to each program when we put this arange here. Yeah, here. So this creates a vector for each program. This vector is calculated once per program, so 4 times in total. Now let's see, when we have that arange and we have that PID times block size plus this arange. So for PID 0 you get 0, 1, 2, 3. For PID 1 you get 4, 5, 6, 7. So it's adding this number to every element of the array. So for PID 3 you get 12, 13, 14, 15. So now each of the programs has this vector according, which one. And then we just go for each of the, so it's going to be executed 4 times in each program separately. And we will take the, from beginning to offset all of them and just save this number. So this store, each program does 4 stores, one for each index in its offset vector. Since there are 4 programs and each stores 4 values, you get 16 stores in total. So let's see, tl.arange happens 4 times, once per program. We have 4 programs. Offset happens 4 times, once per program, so it calculates the entire vector once per program. And then store happens 16 times, so for each number in the vector, each element. So a trick when debugging, you cannot use a print statement directly in the kernel. So what you can do is you can create your main output tensor and the debug output tensor. So the main output will be the same, but the debug here, we are just writing the PID. We are not modifying any values. So for example, I was modifying here offset +1, but in your debug you would just write it like this, so you have like core values to see what's happening, and that's just a trick. And then you can print that later to see if the IDs are correct, if everything is correct in your code. So you will just see the IDs of all of the tensors, vectors, programs, and stuff. So next simple step we will learn, read from memory, do a computation, then store. Let's allocate an input tensor on the GPU with known values, load each value into the kernel, multiply it by 2, store the result. So the code is going to be very similar. This is the same program ID, we only have one dimension, 1D vector, block size 4, that's all the same. So let's see, the offset, it's going to be same. PID times block size plus this vector is same. So here we load, x is tl.load, input plus offset, input pointer plus offset. Then we multiply, y is x times 2, and then we store output pointer plus offset, and we store y instead of this x that we had. So we will just replace x with y, which is 2 times x. So if I run this, input tensor is 1 from 15, but output tensor is 0 from 15, 0 to 30. I think it's very easy to understand if you know what we did by now. This is the same. I mean, this is the same. But then we have this loading, multiply by 2, and then just storing at the same index. Same index. Just the value is different. Let's now add some safety checks. You see how we are calculating offset. But what if this offset number is larger than this 16? So let's see our offset calculation formula. Somehow we make some mistake and we get 18, but the maximum number is 16 in our tensor in memory. We would get an error. So I added this mask. This will make sure that offset is smaller than the number of elements, because number of elements is 16, but offset is the index. So offset goes from 0 to 15. So it should always be smaller than the number of elements. So I added this number of elements here, and I passed it with this input.numel. I'll explain what it is. Just I also put x to load with mask, mask equals mask, and other 0, and storing y with mask equals mask. So let's see what this does actually. So input.numel is a PyTorch function that returns the total number of elements in a tensor. For example, if we have 18 elements in tensor called input, input.numel will return 18. So even if it's a multi-dimensional tensor, 3 times 16, 3 times 6, numel will still give you the total count of elements, so 18. So this mask that we create, it's gonna be true or false. So this mask makes sure the kernel only writes valid positions that are less than the total number of elements. So it can only write within this tensor or read within the tensor. Now let's check this element-wise addition. So we got 2 arrays, normal array from 0 to 17, it's 18 numbers. Second array from 18 to 0, going -1, steps is -1, so from 18 to 0, but 0 is exclusive, so to 1. These two, we want to add them element-wise. We create a new tensor that's like A. So it's going to be empty tensor like A, so same shape as A. Everything should be the same. Let's first take a look at this add kernel. Pointer for A, B for output, number of elements, and block size for each of the threads. So it's gonna be 4. We have the same prevent out of bounds access. So we load pointer plus offset, and mask is mask, and then the offset is gonna be the same. So we just load these two, and result is A plus B, and then store in output pointer plus offset result, and mask is mask. So we already know all of this. You can screenshot this and ask ChatGPT to explain or self-study this if you don't understand. So let's explain this line of code. We have some griddies, lambda, meta, Triton, cdiv and stuff. So this defines how many programs blocks Triton should launch on the GPU. So this is the grid. In Triton, each program handles block size elements. We already know this. So we need to figure out how many programs to launch to cover n elements. So n elements can be 18 and block size can be 4. So we will use this ceiling division, Triton.ceiling division. It divides and rounds up. So 18 divided by 4 is going to be 5. So 4.5, it's rounded up to 5. And this lambda meta, this is a function Triton calls at compile time to decide the grid size. In simple terms, it's just going to be number of programs along axis 0. So launch 5 programs, blocks, each will get its own program ID 0. And the reason it's axis 0 is because we just have one number here. So this will just give us one number. And you see comma and there is nothing, so it just tuple with one number. So it's only axis 0. So one important thing, we have the mask. And if mask is false, so if our sequence is out of bounds, then value 0 or whatever we specify as other is used instead of reading the memory. So now we will just change to float 32 as the data type instead of int 32 that we were using before. And this is more realistic and more commonly used in neural networks. So just where we define the tensor in the Python, not even in the kernel, but just in the Python. So more realistic for neural networks, fully supported by Triton math operations, for example, exp, log, etc. A good stepping stone to mixed precision later, float 16 or bfloat 16. So now let's learn how to use this tl.exp in the Triton. So we're going to create a tensor using torch linspace from 0 to 2. So from 0 to 2 and divide this inside to 18 evenly distributed numbers. So this linspace will go from 0 to 2 and divide into 18 evenly distributed values. We are using these small values so exp doesn't explode, because exp is e to this. So if we have a big value, e exponential value, it will be big exponential result. So everything is going to be the same as the previous example. We just now load this x, okay, and then into our kernel GPU memory, and then y is tl.exp of x, and then we save y, and that's it. So this will, for each thread, it will load this block size. So the whole tensor will be divided to each thread, and these are the values. So I guess e squared would be this, e to 0 would be this, e to 1, which is not really 1, but it should be like this, etc. So first of all, next thing is we should use powers of 2 for block size. It's for better memory performance. GPUs love coalesced memory access, which means threads accessing adjacent memory at once. Using a larger block size that's a power of 2, like 128, lets you use full warp wavefront with 32 or 64 threads, maximize memory throughput. So this is, I guess it works well with hardware, because hardware is divided into these chunks of 32 or 64. And then reduce the number of blocks, lowering kernel launch overhead. Yeah, because larger block size means less of them. So we just have a fewer of them to launch. So here I'm using block size 128 and 1024 of these elements. So I mean, this is gonna be the same thing here. So let's go to the next thing. Now let's see measuring the speed of your kernel. Why? Because you just optimize memory layout with block size 128, and the natural next step is seeing how fast it runs, so you know when you are improving things. So step is add Triton testing do bench to time your kernel. What is do bench? It's a Triton utility that runs your kernel multiple times and returns average runtime in milliseconds. So we will add these two lines of code. After your kernel launch, it will be here at the bottom of everything. So I'll copy it. Instead of this print, I'll just do it like that. Kernel time 0.006 milliseconds, which is very low. So actually, we don't even need this line that's launching the kernel. We are just launching the kernel within this do bench to measure it. Now let's see how we can fuse operations inside of a kernel. This is what makes LLMs very fast, for example, in flash attention and other operations. So let's do a tiny step into Fusion by adding a second operation inside the kernel, instead of doing it after in PyTorch. Goal: fuse two operations into one kernel. Let's say you want to do this in PyTorch. Y is x times 2 and z is y plus 1. Normally you'd launch a kernel for x times 2, get y, and another for y plus 1. But we can fuse both into one Triton kernel. So why fuse? Because fewer GPU launches, less overhead. Data stays in registers, so it's faster, we don't need to move around data, and looks cleaner, less code. So instead of this in our code, y is equal x times 2, and then storing that, we're gonna change it to z is x times 2 plus 1, and then store this z. Now you've done basic kernel fusion. Your kernel does more work per launch, which is exactly what GPU optimization is all about. Now let's fuse this, what we have, with a relu function, and relu of v is just a maximum of 0 and v. So whatever value we have here, if it's lower than 0, we will get 0. If it's larger than 0, we will just get the same value. So replace this, what we have right now, with the tl.maximum of that and 0. So TL maximum is Triton's Elementwise max operation, just like torch maximum. Now we have multiply, add, and relu fused in one kernel. This mimics how real MLP layers are fused: linear, bias, and relu. So now let's create a custom linear layer in the feed-forward network in our kernel. So we have some input, multiply it with weights, and add bias. So we need x to be shape of batch and the input dimension. Weights are shape d out and d in, so this is the weights. And then b is just shape of d out, because we are adding this after we convert this to with the weights. So it's gonna be same as this d out from weights. You can self-study this Ask ChatGPT screenshot, because there is a lot of different knowledge that you can or should know if you don't know it now. Let's go with 16 batch size, d in is 32, and d out is 64. So you can ask more about these linear layers and what they do, but you can also check this. So we will just create these tensors to be random numbers: batch and d in, device cuda, type is float 32. Same for these tensors, d out, d in, and d out here. We need to set d out first and d in, because we are transposing this matrix. We need to transpose, so We'll see. Step 2, write the matrix vector kernel. For now, let's compute one output row at a time. For I in 0 to batch -1, we compute this, which is gonna be for that batch, entire vector in that batch. So we will compute this output by taking the vector in this input batch and computing with the transposed weights matrix and adding bias. We'll write a kernel where each block handles one row of Y. Step 3, Triton kernel, basic matrix multiply with bias. So we have X pointer, this is the input tensor, weights pointer, bias pointer, output tensor pointer, dimensions in, dimensions out, block size M and block size N. So we'll start with the PID. Each block handles one row of output, so batch dimension. So as I said here, block size M is going to be one row. So we are determining how many of the, in the matrix, how much to load into the kernel. So we are going to process one row in each kernel. So it will be dimension 1, so block size 1, and this will be the full row, full one row. So here we will just launch 1D. So B is the number of threads. It's going to be just one dimensional. And in each thread, we will process one row. So whatever the number of rows, I'm guessing. And we will just pass in all these good variables, and that's it. So let's see what those variables are. Block pointers. So within the blocks, we have a row index is PID, because each thread has its own row, so that those are the same. And then column offsets and row offsets. It's gonna be from 0 to N and from 0 to M. So as we said, we are doing full row per thread, so this is not used here. We do full row because block size is just 1. So this will just be the index of the row, which will just go one by one. So we will not create multiple rows. For example, block size M could be 2, then this would, we will have 0 and 1 because we are processing 2 rows at a time, but here we are just processing 1, so it's simpler. So since these pointers, now this is getting more complex, we need to do exercises and learn this by just doing this kind of exercises. So let's leave this for the next video. So in the next video, I will continue doing simpler exercises than this, and we will learn to code together, and we will go to this more advanced step. So thank you for watching. You can check other videos on my channel. You can learn a lot, and see you in the next video.